Hello, everybody. We're into week 7, the final week of our course, and in this week we're going to be covering chapter 9, which is all about gases and how we can measure different quantities around them and manipulate those. Section 9.1's learning objectives. We're going to define the property of pressure. We're going to define and convert among units of pressure. We're going to describe the operation of common tools for measuring gas pressure, and we're going to calculate the pressure from a manometer, which is a type of measuring tool. So it's kind of strange to think about this, but in the beginning, people weren't even sure that air was even really there. And they had some weird ideas about what exactly it was. But by the 18th century, we had pretty much determined that air is actually there and that it is a mixture of gases. It wasn't long after that before we started to put that knowledge to work and develop things like hot air balloons for travel. And with our modern understanding, we have some contemporary issues, including things like ozone depletion in the stratosphere, where we lose this layer of ozone, which is a type of like oxygen molecule that helps protect us from the sun, and carbon dioxide release into the atmosphere that's causing global warming and climate change. So gas pressure, pressure is not just a quantity that gases have. It's defined in physics as any force divided by area. In gases, gas pressure is a result of the force exerted by gas molecules colliding with the surface of objects. In the English system, the units for pressure are pounds per square inch. And one measurement tool that we use is called a mercury barometer. And this is a device that's used to measure the atmospheric pressure. You have to kind of conceptualize pressure a little different than force. In this example here, you have an elephant, which is really large, very massive. It has a lot of force pushing down. But each one of those forces, all that force is distributed across its 4 feet and touching the ground. And that actually exerts the same amount of pressure on the ground as a small ice skater who is balancing on just a single skate. All of her weight is being forced down into a very small area on that ice, and that pressure is actually causing the ice to heat up and melt, which is what lets her slide across the ice. So let's talk about some of the units of pressure. Sometimes, due to the way that we may measure pressure, millimeters of mercury is a useful unit for us to use. Far more commonly, you're going to see atmospheres, where 1 atmosphere is like the normal atmospheric pressure, the pressure that we're experiencing all around us all the time. When we're working in the SI system, the unit for pressure is going to be the Pascal. This is defined as the pressure exerted by a 0.1 millimeter high film of water on a surface beneath it. And that's a really small unit, right? That wouldn't exert a lot of pressure. So we often work in kilopascals or 1,000 pascals. Another related unit of pressure is the bar, where 1 bar is equal to 100 kilopascals. And then we have our pressure conversion. So we can see here that 1 bar and 1 atmosphere are really close to one another. That's also equal to 760 millimeters of mercury, which is equal to 760 torr. Torr and millimeters of mercury are therefore the same unit, which is equal to 14.7 pounds per square inch, psi, which is equal to 101.3 kilopascals. Using these pressure conversions, we can move between whichever units we want, to making conversion factors. So how do we measure atmospheric pressure? A barometer measures pressure in terms of the height of a column of liquid mercury. It doesn't have to be liquid mercury, but traditionally that's what we've used. We've actually moved past using mercury altogether because it's pretty bad for you, and we now have like digital barometers and stuff. But for our learning purposes, we're going to pretend like we're still going to use mercury. The atmosphere exerts a force on the liquid mercury, causing it to rise. The pressure exerted by a fluid due to gravity is known as the hydrostatic pressure. And what that is, so that pressure is going to equal the height that it's risen times its density, rho, times g, which is the acceleration due to gravity, or 9.8 meters per second. Commonly, the pressure of the atmosphere at sea level pushes the column of mercury 760 millimeters high. So here we can see an example of the barometer where we have these tubes that have a vacuum in them, right? So you can imagine almost like a straw where you've sucked out all of the air up there. And we'll see that the mercury rises 760 millimeters, whereas the water would have risen 33.9 feet, which is why mercury was traditionally used in these type of barometers. It's very, very dense, but still a liquid. We know that mercury is one of those, is a very special element in the fact that it is both a metal and a liquid at room temperature. So pressure varies with the height of a column of air above you. We don't notice the atmospheric pressure, but we do notice changes in the atmospheric pressure. So this is like why our ears pop during flights and why mountain climbers get altitude sickness. It's because there is a change in pressure. And we can picture that here. The pressure of the atmosphere is pushing down on a single point, and that point could be measured to be found to be 14.7 pounds on any square inch. So the atmosphere is always pushing down in on you. As we moved up the atmosphere, you're going to have lower and lower pressure until eventually you get up to the exosphere, where the atmosphere is very, very thin on the edge of space. Even on the surface of the Earth, there are variations in the pressure, and that leads to a lot of the climate and weather that we see, where we have air rushing from an area of high pressure to an area of low pressure. So how do we measure a pressure of a confined gas? The pressure of a gas in a flask is measured relative to the pressure of the other side. The other side is typically left open so that the pressure is relative to the atmospheric pressure. The distance and direction that the mercury travels is related to the pressure of the gas. When the pressure in the flask is higher, then the fluid will be higher on the other side. When it is lower, then the fluid will be lower on the other side. So let's actually picture this. So here are our scenarios. We have a closed end with a vacuum. The pressure in this vessel, therefore, has nothing to do with the atmospheric pressure. We can measure it directly by taking this height times the density of the material we have in here, say mercury, times the acceleration due to gravity. What I want to point out to you guys is that when we use mercury, this quantity here is just this height in millimeters of mercury. So if H was 10, this value here would be 10 millimeters of mercury, which is why it's a useful unit. Once we have an open system, we leave another possibility, right? So if this is a vacuum, if there's anything in here, it's only going to push it up this way. But once we have it open, there's the possibility that the atmospheric pressure will be higher than the pressure in the gas, in which case we have this situation where the liquid is being sucked towards the gas and it's lower on the right side. So in this case, we'll measure this height, we'll take the atmospheric pressure, and we'll subtract out the H rho G quantity, the hydrostatic pressure. Now, on the other situation, if the pressure inside the gas is higher than the atmospheric pressure, it's going to rise on this side. And in this case, we're going to have the addition of that hydrostatic pressure term there. Manometers are used in the real world all the time. One of the blood pressure cuff that they use to measure your blood pressure is a type of manometer called a sphygmomanometer. I like that word. In section 9.2, we're going to identify the mathematical relationships between the various properties of gases, and then we're going to use the ideal gas law and related gas laws to compute the values of various gas properties under specific conditions. So there are a lot of different types of gases. These can be single elements like noble gases like argon or helium. They could be a diatomic element like hydrogen, nitrogen, or oxygen, or they could even be compounds like CO2, carbon monoxide, water, or ammonia. All gases, though, have the same dependence on four properties: volume, the amount, which we'll describe as N, usually the number of moles, the temperature T, and the pressure P. The pressure of a gas is directly proportional to its temperature in Kelvin. At a constant volume and a number of moles, P is going to equal kT. This means that they have a directly proportional relationship when we write it this way. This is known as Manton's law or Gay-Lussac's law. And we can picture what that means here. So when we cool down the gas, it's going to have a low pressure. We heat it a little bit, it gets to a higher pressure. And then when it's very, very hot, you're going to have even a higher pressure. So as we increase the temperature, we also increase the pressure. If we graph that out, we're going to see that as a straight line, a linear relationship between pressure and temperature. The volume of a gas is directly proportional to its temperature in Kelvin as well. At a constant pressure and number of moles, the volume is going to equal some constant times the temperature. This is Charles's law. And again, if we graph that, we're going to see a straight linear relationship between the volume and the temperature. The volume of the gas, though, is not directly proportional, but inversely proportional to its pressure. So at a constant temperature and number of moles, we're going to have that the pressure is going to equal some constant divided by the volume. This is known as Boyle's law. And if we graph it out, we're going to see that there is this curved rational function, 1 over x function that you may have learned about in your math courses. If we, however, wanted it to be a line, we could always graph either 1 over p here or 1 over v here, and that's going to make it look like an actual proper straight line. The change in volume is actually how you breathe. So when you push down on your diaphragm, your lungs expand. This causes an area of low pressure. Air flows in, then you contract it, create higher pressure in your lungs, and push it out. The volume of a gas is directly proportional to the amount of gas. So if we hold the temperature and pressure constant, we have that the volume is equal to, again, some constant times N. This is known as Avogadro's law. If we look at these four relationships and we want to combine them together, the simplest way that we can do that is something called the ideal gas law. And it's PV equals nRT. So pressure times volume is going to equal the number of moles times R times the temperature, where R is a constant that is an amalgamation of all of those other constants in these other formulas up here. R has a value. It is 0.08206 liters times atmospheres per mole Kelvin. You can look up R on Wikipedia and see that it can have many other units. So depending on your calculation, you may want to use a different one, like say have bars instead of atmospheres or kilopascals or something like that. So what is the ideal gas law? The ideal gas law accurately describes the properties of an ideal gas, a hypothetical construct. So ideal gases are not ones made of atoms or molecules that take up any space, and they do not interact with any other matter. So we're going to assume that the things that make up the gas don't take up any they don't have any volume themselves, and they're not going to interact with themselves or anything around them. No gases are ideal, but under certain conditions we can assume ideal behavior. What are those conditions? The gas must be at a low pressure. They should have a high temperature, and these conditions combined together are going to result in a dilute gas comprised of fast-moving molecules. And if you think about it, that kind of makes sense, that we can assume that they're not going to interact with each other when they're moving really fast and they're nowhere near one another. Also, if it's very dilute, there's not a lot of gas in there, then the volume of the actual gas particles is going to be pretty small in relationship to the container, and you could assume that it would approach zero. Sometimes it's important to define standard conditions. So standard temperature and pressure is something you'll see a lot, STP. And this is defined as 0 degrees Celsius and 1 atmosphere. You should note that IUPAC recommended value of standard pressure was changed to 1 bar in 1982, but many texts continue to use the 1 atmosphere value. At STP, the volume of 1 mole of ideal gas is 22.4 liters. So we can picture that here where we have all of these balloons. They're all under standard conditions. They all are exactly 22.4 liters, but each one contains a different mass of atoms because each one of the atoms weighs a different amount. In section 9.3, we're going to use the ideal gas law to compute gas densities and molar masses. We'll perform stoichiometric calculations involving gaseous substances, and we're going to state Dalton's law of partial pressures and use it in calculations involving gaseous mixtures. So we're going to recall that our molecular weight is the mass of something divided by its how many moles there is of it. And rearranging that, for moles, we can see that the moles of something is the mass of it divided by its molecular weight. If we substitute in the mass divided by the molecular weight for N into our ideal gas equation, we get this equation now, where PV equals the mass times R times the temperature divided by the molecular weight. If we choose to look at this as the mass divided by the volume times RT over the molecular weight, we get this M over V term. And if we recall, that is the density, the mass divided by the volume. Substituting in that density, we get this equation. And then rearranging and solving for the density, we can see that the density of a gas is the pressure times its molecular weight divided by RT. So density is an intensive property. We're going to remember that. That means it does not depend on the size of the system. But the density of an ideal gas does depend on the pressure, temperature, and molar mass. We can also solve that equation for the molecular weight. And we can see that the molecular weight is equal to the density times the ideal gas law times the temperature divided by pressure. Or we can substitute in our value for density here. If we have the mass and volume, we can see that that is MRT divided by PV. We can measure the mass of a gas pretty simply doing some experimentation. We can measure a flask that is sealed at the top, inject that gas into it. It is typically then condensed, so we cool it way down until it condenses into a liquid at the bottom, and then we reweigh that flask. Dalton's law. So the ideal gas law also applies to mixtures of gases if the gases don't react with one another. And this leads us to Dalton's law of partial pressure, which is that the total pressure of the system is going to be equal to the pressure of each one of its components. So if you have A in a flask and it has a pressure, B in a flask and it has a pressure, you add them all up to get the total pressure. The pressure exerted by each individual gas in a mixture is called its partial pressure. The partial pressure is equal to the pressure that the gas would exert if it was all by itself. And we can picture that here. If we had 3 containers, each with a different gas in it at a different pressure, when we combine them, if we combine them all together somehow into a different tank, its pressure is going to be the summation of all those pressures. So now I want to introduce the mole fraction. This is a type of concentration. It is expressed as the fraction of moles of a particular component in a mixture to the total moles of all components. So if a mixture contains A, B, and C, the mole fraction, this is a capital chi, a Greek letter, of A is going to be the number of moles of A over the total moles of A, which would be the summation of A, B, and C. Similarly, we could have the mole fraction of B and the mole fraction of C. If we know all of the mole fractions of all of the components, then they will sum together to equal 1. And we can see that expressed here using sigma notation. When only the total number of moles is known for the mole fraction, it can still be expressed as the moles of any particular component over the total number of moles. This can be rearranged to yield that the total number of moles of A is equal to its mole fraction times the total number of moles, which is how this operates as like a concentration unit. So let's extend this logic to Dalton's law now. We can express the partial pressure of a gas in a mixture in terms of its mole fraction. So we can say that the pressure of A is equal to the mole fraction of A times the total pressure in the system. And we could do the same thing for B. If we then have Dalton's law and we make these substitutions in, we can see that the total pressure is equal to the mole fraction of A times the total pressure plus the mole fraction of B times the total pressure, so on and so forth. So a common way to collect a gas is to collect and quantify it by capturing it over water. This can be done pretty easily and pretty effectively, and it's the way that they've been doing it for a long time. But it does come with a caveat in that that gas is going to pick up some of the water that it's bubbled through. So if we imagine a gas is escaping here and it's being trapped up in here, it's going to pick up some of that water vapor. And in doing that, we're going to have to make a correction. So we refer to the gases collected over water as wet gas mixture. The pressure of these gases must be corrected to account for the water they contain. Say, for example, that the gas being collected was H2. The total pressure that we're measuring is going to equal the pressure of the water that's in the gas plus the pressure of the H2. We know from Dalton's law that these would sum together to give us the total pressure. And we have a special name for the pressure of the water. It's known as the vapor pressure of water. The pressure exerted by water vapor in equilibrium with water in a closed container is the vapor pressure of water. This is an intensive property that does not depend on the amount of water, but it does depend on the temperature. So basically, we know what the vapor pressure of water is at any specific temperature. So we just have to go and look up for our temperature of our experiment what that vapor pressure is in order to get that term and make the correction. Stoichiometry and gaseous reactions. Gases may appear as reactants or products in a chemical reaction. The ideal gas law and a balanced chemical equation can be used to relate the pressure, volume, temperature, number of moles, and grams of a gas that takes part in a chemical reaction. Stoichiometric factors can be used to relate the moles of one substance to the moles of any other substance in a balanced chemical equation. So we were figuring out moles before, and now we have an equation to relate the moles to the pressure, volume, and temperature. So this allows us to do some different, a little bit more complex calculations. So one thing to look at is the volume ratio. The volume ratio of any two gases in a reaction at constant temperature and pressure is the same as the stoichiometric ratio, mole ratio, in the balanced chemical equation. So that means that the volume of gas A over the volume of gas B is going to equal this. We saw that earlier when we were deriving the ideal gas law. If we cancel those K values, we can see that this is equivalent to the number of moles of A over the number of moles of B. Here we can picture how stoichiometry can work out. As we see here, before when we were looking at different molecules, we could just picture those as groups of atoms that were contained in little systems that move along. And this also, interesting at the end of this chapter, is a little talk about climate change. So now with everything that we've learned, we can talk about this a little bit. We are on the Earth, and we are surrounded by all of these gases. And the sun shines down its radiation on us. And this is high energy radiation, right? This is high electromagnetic radiation. So some of it bounces off, but most of it actually has enough energy to go all the way through. After it hits the Earth, it excites some electrons, and then it's going to emit radiation that's of lower energy. This is mostly in the form of infrared radiation, and that doesn't have enough energy to exit the Earth when we have a thicker layer of gases on the outside. And that's what causes the Earth to eventually heat up. It can't get rid of the infrared radiation that it's emitting fast enough to maintain its temperature. The rise in carbon dioxide levels are pretty undisputable at this point. And we'll give a little shout out to Susan Solomon for her research in doing in climate change. And there's a nice little blurb about her in the book. In section 9.4, we're going to define and explain fusion and diffusion. And then we're going to talk about Graham's law and how to use it to compute relevant gas properties. So a little recap here. What we experience as gas pressure in macroscopic domain is due to gas atoms and molecules colliding with objects and each other in the microscopic domain. When these collisions are frequent, or the gas atoms have a lot of kinetic energy, we experience a high pressure. And we're going to recall that the kinetic energy of a gas is directly proportional to its temperature. So one way to describe the frequency of collisions is to talk about the distance a gaseous atom or molecule travels without colliding. This is known as the mean free path. The mean free path is the average distance a gas or atom molecule will travel in a particular system before it hits something and collides. It is typically hundreds of times the diameter of a gas molecule. Diffusion. So whenever possible, matter is going to spread from an area of high concentration to an area of lower concentration. To put this in more scientific words, the matter moves across a concentration gradient from an area of high concentration to an area of low concentration. This process is called diffusion. Some examples are like smells spreading through a room or a drop of food coloring spreading through a glass of water. Because gases are moving rapidly and freely, they will quickly spread through the container. And diffusion only stops when the concentration of gas is uniform throughout the container. So We can picture this here if we had hydrogen in the left chamber and oxygen in the right chamber and a closed stopcock. We open the stopcock, allowing the two systems to come in contact. Some of the hydrogen moves into the right chamber, some of the oxygen moves into the left, and after a long time, relatively long time, we get an even distribution of hydrogen and oxygen in the two chambers. The rate of diffusion is the amount of gas passing through an area per unit time. So we have rate, and we have an equation here for this. Actually calculating the rate of diffusion is kind of tricky because it depends on a lot of factors. The magnitude of the concentration gradient, the amount of surface area available for diffusion, the distance the gas molecules must travel, and the velocity of the gas molecules. Effusion is the process of a gas moving through a small orifice. It's similar to diffusion, however, the two rates are not the same. Graham's law of effusion relates the rate of effusion to the atomic mass of the gas. So we can see that here we have the rate of effusion, and this means that it's related to, and not necessarily exactly equal to, 1 over the square root of the atomic mass of the gas. We'll note that the rate of effusion decreases as the mass of the gas increases. So here we have diffusion throughout the container, and we're picturing effusion as there's a barrier with a small orifice and some of the gas is allowed to go through it. We can do some calculations with Graham's law. We can calculate the ratio of the rate of effusion of helium to the rate of effusion of argon. So one compound to another. And if we divide those two rates and do a little math, we'll see that that's going to be equal to the square root of the atomic mass of argon divided by the square root of the atomic mass of helium. Note that here helium is in the numerator and it appears in the denominator on the right hand side. If we plug in those values that we already know, we can get that the ratio of those two rates is 3.159. So let's go through an example where we can get some useful information from that. So here we have two identical balloons are filled with the same pressure and volume while being held at the same temperature. One is filled with helium, the other with argon. The argon balloon takes 4 hours to lose half of the moles it contains, N. How long will it take for helium balloon to lose the exact same number of moles? So the first thing we need to do is to relate the rates of effusion to the time it takes for the effusion process to happen. So the rate of helium effusion is going to be the number of moles that travel divided by the time that it took, and the same for argon. And our problem, we said that it was going to be the same number of moles. How long does it take for the same number of moles to come out? So these two ends are the same. We can cancel those and we get this relationship here. If we clear those complex fractions, we get the time of argon divided by the time of helium is equal to 3.159. Plugging in the time that it took for the argon to effuse out, we get this relationship here, and then solving for the time of helium, we get this, and we see that it would have taken the helium 1.266 hours, which is what we would expect. We'd expect that a molecule with a lower atomic rate is going to effuse quite a bit faster. If we picture that, that's pretty much what's happening in the case of a balloon. Gas is slowly effusing out through tiny orifices in the surface. If we had argon and helium, or helium and argon, we would see that the helium starts to effuse out quite a bit faster. And effusion is also the means by which they enrich things like uranium. In this case, we are enriching uranium hexafluoride by basically putting it into this giant centrifuge and then allowing it to spin really fast, and it goes through a selective barrier, and we wind up with getting enriched uranium if fusing through at a faster rate and purifying the gas.